All right, welcome back to our next lesson. Today we're going to be studying when backtracking doesn't work. We've lately been focusing on equations where we can work backwards because it has like a exact ending number to figure out where I started or figure out the missing value, right? And not all equations work that way. So our mindset message today is that struggling grows your brain. I want to remind you this again. It's actually really important for your mind to spend time struggling through something and then finally overcoming that. Because your neurons, those cells in your brain, they make new connections and it literally grows your brain. The number of neurons that you have, I should say. Not the size of your brain, I suppose. Our learning goals today, you want to be able to understand the limitations of backtracking. And we will use visual models to help us solve equations when we can't backtrack. Prior knowledge, you do need to remember how to use backtracking to solve equations, as well as just generally operations on numbers. Let's dive in. Let's consider this equation here. 3x plus 4 equals x plus 8. If we were to do a number trick for this, if we start with this, we usually like to read it left to right most of the time, right? So it says choose a number, multiply 3, add 4, and then over here is our ending number, right? But the problem with this is, if we just said our ending number was 8, right? If this was just 3x plus 4 equals 8, oh, we could totally backtrack that because we could just take 8 and we could subtract 4 and then divide by 3. But this says 8 more than your starting number. So it's annoying because our starting number is what I don't even know, and if that's in my results, there's no way I can go backwards because I need to know what that number is, right? So number tricks are not very useful all the time, or backtracking, right? Because we use number tricks to think about backtracking. So this is red for a reason. It doesn't really work all the time, and we're going to have to put that on pause. It's useful and it's great to help us understand those other equations. Now let's look at two that are very helpful, visual models to solve equations like this one. So the first type of visual model we've seen in our recent puzzles that we've been playing with is what we call a mobile. Now you can think of it like a seesaw because this represents up here something that has to be in balance, right? So if it's flat, if it's horizontal like this, what we're saying is that we intend this to be balanced. So what that means is this side weighs equally as much as this side does. So the nice thing about this visual is it really helps us actually understand how we can work with equations. And I've set this up in such a way, this here essentially represents the equal sign, okay? The fact that it's balanced means that it's equal. So we have this equal sign, and what we have on either side of the equal sign is 3 somethings plus 4. That needs to weigh the same as one of those things plus 8. So you can kind of see this. Here's my 4, and I've kind of split the 8 into 2 4s. Now, what if you had something like 4, and what if instead of 8, what if this was 7, and it doesn't split into 4s easily? You could certainly just think of this as a bunch of 1s, okay? That would work. But the nice thing about this is, it's really easy to tell if you need balance what you can do. If I take something off of this side, it's going to become too heavy on the other side. So to keep it balanced, I must take an equal amount off of the other side, right? So here's the cool thing to remind you of. We can see things that are matched up. Do you see that we have a 4 here? We can take a 4 from there. And then we have one of these x's and one of those x's we could remove and it will stay balanced. So if you watch this, taking that away, I must take that away, and we're still balanced. Good. And I can take this away, but I must take the equal amount away from there, and I'm still balanced. So we can solve equations like this using these kind of models, and we can kind of reduce it down in our head, actually. Because look what I'm left with. It's still balanced, it still represents the same relationship, but I know that 2 of these must equal 4. And I can think, oh, so in my head, what is that x going to equal? Well, if 2 of those equal 4, I can easily see that one of those x's equals 2. That's a really nice way to help us figure out an equation like that. A third way to visualize this equation is using a number line actually. So let's say right here is 0 on the number line, and this number line just goes along. Well, we can kind of think of this 3x plus 4, and it doesn't really matter which one you put on the top and bottom, as you're making 3 jumps of something, and then you're jumping by 4, and you end in the same place as if you went 1 jump of x and then jumped 8. Does that make sense? So the equal sign in this case, shows up right there in the fact that they end in the same spot as each other. And we can kind of do some deduction here like we did with the mobile puzzle with this one. And you'll be able to see some connections here. Do you see how if I'm going 3 x's and this one's going 1x, once they both jump an x, they're in the same spot there, right? So we can say that this distance here, whatever's here and here must be equal. So we can kind of reduce it and say that, oh, 8 must be the same as 2x's plus 4 more, right? But also you can think here, if this much is 4, then part of that 8 is already taken up. So I can draw a little bit extra in here and I can say, okay, well, if this much was 4, how much is this if the whole thing's 8? Oh, that also must be 4, because 4 plus 4 makes 8, right? And from there we can deduce, okay, well I know that 2 x's must be equivalent to that 4. Oh, that means one of those x's, we just split it in half, that means one of those x's has to be 2. And we got the same thing using those methods. Using backtracking and a number trick doesn't really work. And this is really helpful for us to really get a good foundation for equation solving. Let's have you try a new equation and make each of these kind of models yourself. Okay, I forgot to label the last problem, problem number 1, so you can do that. Now on to number 2. So I want you to use a mobile and a number line model to solve the equation x plus 9 equals 4x plus 3. So the mobile, you're going to start, and then the number line. Let's start with this. Let's first have you pause and draw out the setup for each one first, and then we'll check that you set it up correctly. Then afterwards, you can actually use the model that you made to solve it, and we'll check that you solved it correctly. So right now, pause, and I want you to draw out the model for the mobile, and then draw out the model for the number line. Okay, so let's go ahead and check that you set it up correctly. Now, I split the 3 and the 9 can be split. So again, you don't have to do 1, 1, 1, 1, 1. I thought of the 9 as 3 3s and then 1 3 here. Okay, so you see this is x plus 9 and this is 4x plus 3. Exactly how our equation is. And then for the number line model, same deal. The top represents the left side of the equation and I made the bottom represent the right side. Doesn't really matter, you could flip-flop it. But either way, what I have is 4x's and 3 more equals, right, ends at the same place as 1x and 9 more. So double check that for yourself, make sure you kind of understood how we set that up, and then now go ahead and pause and solve the equation using both of these models. Okay, let's check that you solved these correctly. Remember that with this one it's nice because to keep it in balance, I can drop some weight off of one side as long as I drop equal weight off of the other side, right? That's nice. So I can also drop one of these guys off if I drop one of those off from there. So now what I have here is 3x's equals, and that looks weird, it's 2 3's, but it's actually 6. You can certainly just realize this is 6, right? So if 3x's equals 6, then each of those x's must be 2. Hey, wait a minute, that's exactly what we got before. Now let's take a look at this one. We can do some similar reasoning here. Remember that we can kind of realize that this x is kind of, doesn't matter here because they're the same. So we can just think, okay, well, if this much is 3, what's left in here if that total is 9? 6. So what I have here is that 3x's is the same as 6. Oh, same idea as what I reduced that to. x must equal 2. So there's my solution for that equation, thought about in those two ways, okay? Now most of this, when you do the practice yourself, most of the time you're not going to need to set up these all by yourself, but you just want to get used to that, as well as realizing how that model connects with the equation, because it's really helpful to think of it in that way. So let's move on to a few other things before we finish. So our next thing to think about here, models aren't perfect, you know? Neither of these, the number line or the mobile puzzle model, they're not going to work nicely in every situation. So we're eventually going to get to the point where we have tools and methods where we don't have to use any of these things to solve. But again, these really build a conceptual framework for us for how to work with equations properly. So let's think about this. Which model seems best for this equation? There's one thing about this equation that makes it different than the other ones we've looked at, and that is this. This has subtraction in it, or negatives. And so far, that seems to be a little weird. It turns out that a number line will probably work a little better than the mobile puzzle, because it just seems weird to have a negative amount of weight on the puzzle. Although now that I think about it, you can almost think of it as like a balloon with helium in it that's rising. So you maybe could think of a mobile puzzle in that way, actually. I just thought of that. But let's look at a number line model anyway. So I tested it out, and I looked at this if I tried to make a mobile puzzle. And like I said, if you think of tying a balloon to float up and help it out, it still doesn't really help us that much, actually, because we can certainly erase 2 of those as long as I take away 2 of those to keep it balanced. But it still makes it kind of hard to know what on earth to do with this, right? So this one's just not really going to work super well. Let's jump over to our number line here, which actually does work better. What we're saying here is, if we have 7x minus 3, 7x, let's just assume we're jumping forwards, but then minus 3 means we're going backwards to meet up with this one. And that's 2x plus 7. So we can kind of deduce that a little bit, but it still makes it a little bit tricky to do, to be honest with you. You know what I'm saying? Because what we can do is we can say, okay, well, I have this here, and I can ignore this and this because they match up. And what I like to do is to think of this distance. So let's see, what color should I use? The nice thing here is, if this is 7 and this had gone back 3, hopefully you can see that still this total distance, if that's 7 and that's 3, that total distance is 10, right? And if that total distance is 10, don't forget that that's equal to all those x's exactly. And there's 1, 2, 3, 4, 5 of those there. So this helps me see, oh, 5 of those x's equals 10. So x must equal 2. Yet again, I like the number 2. Okay, so this can be very helpful using that number line. Why don't you try one on your own that has a negative, and then we'll wrap up with a few other equations. All right, I want you to try one out like the last one we did. Use the number line to solve. 4x plus 1 equals 6x minus 5. You notice we have the minus there. Pause right now, set up the number line, and then we'll check it together. Let's check and see how you did. So we have 4x plus 1 should be equal to 6x and then go back 5. We should end in the same place, right? So we know that this distance here must be the same as these 2 x's here, right? Well, if that's 1 and that distance is 5, what's the total amount? 6, right? So we can see that those 2 x's must make 6, and so x equals 3. I tricked you. I didn't do 2 again. So in this case, x equals 3. So I hope you have a little bit of a handle on how these work, and especially, more than anything else, being able to look at the diagram and solve it from that diagram. Let's end with a few equations I want you to just solve in any way you want, and then we'll be done for today. So we're going to wrap up today by just having you solve a few equations in any way you like. try to avoid just guessing and checking. I really want you to actually try to think about the ideas we used. You don't have to physically write out any of the models or anything, but think about how they worked, okay? So go ahead and pause right now and attempt this for yourself, and we'll look at them together. Okay, let's go ahead and take a look at these. So, if 2x plus 4 equals x plus 8, remember this has 2 x's and that has 1 x. I can take an x off of each of those and it'll still stay in balance, right? So if I take an x away here, then I'm going to end up with 1x plus 4 equals 8. And if I take 4 off of this, remember the whole goal is to identify what x equals. If I drop 4 away from this, I can drop 4 away from that, and I get x equals 4. And we're going to officially talk about some of the more formal steps that we use in our next lesson. So I'm not going to say you had to do this a certain way. Same idea goes with this one. This has 6 x's, and that has 1 x. I can take one of those away. I can remove one of those. And this leaves me with 5 x's plus 2 equals, that x was removed, so it just leaves me with 10. Well, if this has 2 over here, this also has 2. So I can drop 2 away from there and drop 2 away from there. And it leaves me with 5x equals 8. Now this one's a little weird because we haven't had equations really yet where we've had weird numbers. If I have 5 times something equals 8, what we're saying is 8 needs to be split into 5 pieces. So it's okay if you didn't quite get this fully right in the end, but this actually goes with division, and we can say that x equals 8 divided by 5, or if you wanted to write it as a decimal, that would be 1.6. Okay? Now C might be the trickiest, I don't know, but you maybe realize we haven't seen equations that have the distribution in it involved. So you'd be right if you guessed that we want to distribute the 2 across the x plus 3. So don't forget that it gets distributed into both. So 2x plus 6 equals 8x minus 6. Okay? And if we were to deal with these, we could take 2 x's away from both of these, right? And it leaves me with 6 equals 6x minus 6. I didn't really mean to do the 3 6's. Oh well. And if you want to deal with this, there's lots of ways you can deal with this, but if you think about the fact that this was minus 6, or if you wanted to set up a number line for this, you'd see that this minus 6 can, if I do something to one side, right, I can do it to the other. So I could add it. You can also, from here, you can backtrack. We already know backtracking, so maybe that's the easiest. Since that was minus 6, we'll add 6, and we'll get 12 equals 6x. And then if I divide that, I get x equals 2. So here are my solutions for these 3 equations. And as I said, we will, in coming lessons, learn the more formal way of writing out all the steps for solving equations. And we'll be able to tackle any kind of equation, even if it's got weird, ugly numbers, whether it's backtrackable or not, using the foundations we've laid. So that's it for today. Happy math, and we'll see you guys next lesson.